Hello everyone. In this video we will talk about optimization in two variables. So in single variable calculus we had two main theorems that helped us find maxes and mins of a function. So the first is the extreme value theorem. So it is the one that tells us when we can guarantee that we will have absolute extrema, right? So if f is continuous on a closed interval, then we know it's going to have a max and a min on that interval. And then the second will tell us where that can occur. So we know if we have a local maximum or minimum at a point, say x naught, then one of these three things must occur. So either the first derivative is 0, and then we would call x naught a stationary point, right? And sometimes you would see critical point, although that would usually lump in the case in 2 as well, where f prime could not exist, right? Your classic example is the absolute value there at 0. Or the max happens at an endpoint, right? So if you cut off your domain and have this closed interval, then you can have something on the boundary there be a max or a min, even if the derivative is not 0. So a natural question to ask then would be, can we find analogous results when we have a function of two variables, right? So if we have a function of both x and y, can we say these same things? So first, let's actually define what it means to be a max and a min again, just to make sure we know what we're talking about. Okay, so we say it has a local max or min respectively if at x naught, y naught, if f of x naught, y naught is greater than or equal to f of x, y, so basically your z value, your height is greater than or equal to the height around you for all points near, and this is kind of in quotation marks what we mean by near your point x naught, y naught. And for a local min, right, we would just switch that inequality to less than or equal to. So let's actually draw a little picture and see what this really means, because near is a little bit different in 3 dimensions than it is in 2 dimensions. So for an example, let's look at the level curves of this function. So essentially, right, we start at height 0 and we're out with this circle of radius 3, and then we keep going up. And so what we're really getting here is like a bowl shape, or I guess really a dome, right, like an overturned bowl. And this top point is above 0, so this is the point 0, 0, 3. And then all of these guys are at z equals 0 and the circle of radius 3 on the xy plane. So we see a pretty clear max, and then all of these would be mins, so around this whole circle. But how do we see this in terms of our definition, right? So the way I like to think of this is, okay, so I said this is a max here at 0, 0, because I'm really just talking about my domain, right? And so if I just go a little bit away, nearby, I can go in any direction I want from 0, 0, then I'm going to be subtracting stuff away from 9 in here and therefore getting smaller, right? So if xy is close to 0, 0 but not equal to it, then I'm going to be getting a smaller value than 3. And similarly, if I'm out here on my boundary, right, then I had 0 in here. If I go in a little bit, then x squared plus y squared is less than 3, so I'm subtracting away, or x squared plus y squared is less than 9, so I'm subtracting away less than 9 and therefore getting a positive number, and thus this is a min all the way around the outside. So it turns out that the extreme value theorem actually still holds. So we kind of saw the example with the last one. So if f is continuous on a closed bounded region, so your domain is a subset of the xy plane, and so for us there, our domain was exactly the circle x squared plus y squared equals 9, the circle of radius 3. And then, we could have anything on the inside too. So this would have been our R. And what we saw was we had an absolute max. That was here. This is our max. And then we had mins all the way around the outside. And those were along the boundary. Okay, and so we'll be less concerned with this theorem, mostly because this closed bounded definition and the proof of this theorem are a little bit beyond this course. But the result, where you find them, that is what we will focus on more. Okay, so here is our analogous result to the second theorem we talked about, right? So if we're defined on some region R, don't have to be continuous necessarily, and we have a local max or min at the point x naught, y naught, then either it's at a stationary point, which in this case will mean that both partial derivatives are 0. So that's our analog of just having derivative be 0. The second case is that at least one of these partials does not exist. That would be kind of your sharp point kind of thing. Or the last case would be that your point lies in the boundary, right? So like we saw with our first example. So the minima all were on the boundary. So let's see that this truly lines up. So for the function that we considered, let's see that this max, let's look for the stationary points and see if we would have found our max without knowing about the level curves. So our partial with respect to x is negative x over the square root of 9 minus x squared minus y squared. And the partial with respect to y is similar because this is symmetric. And so, well, when are these 0? Well, this is 0 if and only if x equals 0. This is equal if and only if y equals 0. So both are 0, or basically we have a stationary point, only at the origin. And it turns out, right, like that is where we found the max to be. But this isn't justification, right? So we have the same issue that not all stationary points will give us a max or min. And we will see an example of that here with our next example. But first, let's also look for other points, right? So the other issue is things on the circle of radius 3 do lie in the domain. They just make it 0, but they are where fx and fy do not exist, right? So fx and fy, d and e, if x squared plus y squared equals 9. And so basically all of the points on the boundary down below are points where these derivatives did not exist, and so these would also be points that we would consider and look for maxes and mins on. Okay, so let's look at one more example here. So in this case, gx is y, gy is x. So this one's very simple, right? So our only stationary point is, again, the origin. But is this a max or a min? Let's look at the level curves really fast. So the level curves look something like this. And so if you notice, then if we just kind of drift out either in any direction from the origin, then we can either go down if we go into the second or fourth quadrants, right? We're going to z equals -1, z equals -2, or we go up if we go in the first and third quadrants. And in either case, right, this is not going to be a max nor a min because we're able to go down or up if we go in some direction from the origin. So this is actually not a max or a min. So for your first exercise, I just want you to find the stationary points for x squared plus y squared. So a natural question that may arise after seeing that origin was not a max or min for the function x, y, you may wonder, like, do we have some ability to determine without like looking at the level curves or whatever to know if a stationary point really is a max or a min? And the answer is yes, we do have a way. And it's basically an analog of the second derivative test from single variable calculus. So first we have to define this thing d, which is fxx, fyy minus fxy squared. So this is why I introduced second order partials last time, because it's necessary in the second derivative test. And this big D stands for determinant, but until linear algebra, you won't really care much about that. And then the second derivative test is as follows. Okay, so first we assume we have a stationary point. Okay, so we're starting with a stationary point, and we just assume we have continuous second partial derivatives. So for all the nice functions that we usually will deal with, this will be true. Then if D is greater than 0 and fxx is greater than 0, you could also look at fyy, by the way, then f is going to be concave up like in all directions, right? So concave up is very obvious if you are in 2 dimensions, but in 3, right, you can rotate 360 degrees. So this means it's like concave up in all directions. So this would be like a bowl shape, right? So it locally looks like a bowl here. And so you would have a local min. Here, you would be concave down if D is greater than 0, but fxx is less than 0 there. It's concave down, so you would have a local max. If d is less than 0, this basically means that you don't have the same concavity everywhere. So basically somewhere it's like concave up, and then somewhere else it's kind of concave down. And this is what I mean by like a saddle point, right? So like a saddle, you kind of like sit in the saddle, it goes up that way, but then like toward the side, it's concave down. And so this is why it's called a saddle point. So this is neither a max nor a min. And if d equals 0, just like in the second derivative test for single variable, we just don't know. We would have to do more work. So now that we have the tools, I want you to verify that 0, 0 is a saddle point for that function xy. I claimed it was not a max or a min. I want you to use that second derivative test. So basically you should be finding d and then checking its sign to verify that this is a saddle point for that function. All right, thank you for watching.